Welcome, everyone. Today, we'll explore communication ports, the vital connections that enable microcontrollers, sensors, and computers to exchange information seamlessly. In mechatronics, effective communication between system components is fundamental for coordination, data sharing, and precise control. As sensors and actuators become increasingly complex and functionally integrated, communication ports provide an efficient and standardized interface that allows these devices to operate as modular, interoperable units. Throughout this session, we'll examine both serial and parallel interfaces, discuss key standards such as UART, SPI, I2C, CAN, and Ethernet, and compare the advantages of wired and wireless communication systems. This lecture aims to provide you with the fundamental concepts of communication, enabling you to interface effectively and reliably with various devices through these ports. Microcontrollers communicate through several types of ports: digital I/O4 on-off signals, analog input-output for variable voltages, and communication ports for data transfer. The communication group can be classified into serial and parallel types. In serial communication, data is transmitted one bit at a time, while in parallel communication, multiple bits are sent simultaneously. Most modern microcontrollers favor serial communication because it requires fewer wires and offers better noise immunity. Today's microcontrollers often allow a single physical pin to serve multiple functions: digital I/O, analog input, analog output, or various communication roles. For example, pin 0 of the RP2040 can be configured as a digital I/O pin, an SPI-RX, an I2C-SDA, or a UART-TX line. This flexible pin multiplexing provides developers with more design freedom, especially when working with limited pin counts. In the RP2040, serial communication interfaces include SPI, I2C, and UART, each optimized for specific data exchange scenarios. There are numerous communication standards, such as RS-232, serial, SPI, I2C, USB, Ethernet, and CAN, among many others. Each of these standards is designed for specific applications and operating conditions, some for long-distance communication, others for high speed, robustness, or simplicity. Understanding the underlying concepts of these communication methods is essential, as it enables you to select and implement the most appropriate interface for your system, ensuring reliable and efficient performance. When selecting a communication method, we must consider several key features: speed, range, wiring complexity, topology, power consumption, reliability, and cost. For example, Ethernet offers high speed and security, while I2C is slower but much simpler, requiring only 2 wires. CAN provides robust error handling and is ideal for noisy environments such as automotive systems, whereas UART remains popular for its simplicity and ease of use. Communication protocols always involve trade-offs between performance and implementation costs. Performance factors include speed, transmission distance, latency, number of connected devices, and power efficiency. Implementation cost depends on factors such as wiring complexity, number and quality of wires, and the effort required for setup and maintenance. Parallel communication transfers multiple bits simultaneously across several wires, making it suitable for short distances, such as internal buses on a circuit board. In contrast, serial communication sends data one bit at a time over fewer wires, which makes it more efficient and reliable over longer distances. That's why modern standards like USB, Ethernet, and PCI Express primarily use serial communication. It simplifies wiring while still achieving high data rates through advanced encoding and timing techniques. In theory, both data rate and throughput can be increased either by adding more wires in a parallel bus or by increasing the clock speed in a serial link. However, raising the clock speed is generally easier and more scalable than adding physical connections. As a result, serial communication has become the dominant choice in modern digital systems. Serial links can operate in different modes depending on the direction of data flow. A simplex connection allows one-way communication only. Data flows in a single direction. A half-duplex link supports two-way communication, but only one device can transmit at a time. In contrast, full-duplex communication allows both devices to send and receive data simultaneously. Half-duplex and simplex systems typically use a single data line, while full-duplex systems require separate lines for transmission and reception. If high speed and reliability are critical, full duplex is usually the preferred choice. However, since the number of wires directly affects hardware complexity and cost, simplex or half-duplex configurations may still be suitable for simpler or low-cost applications. This configuration, 9600 baud, 8 data bits, no parity, and 1 stop bit, is one of the most common setups used in serial communication. It represents an asynchronous mode, where both devices rely on their own internal clocks rather than sharing a common clock line. There are two main concepts for synchronizing timing between the sender and the receiver: synchronous and asynchronous communication. In synchronous communication, an additional clock line is used alongside the data line. The receiver samples data based on the clock signal, often at each rising or falling edge. This provides precise timing and allows for very high data rates, limited only by the physical characteristics of the hardware. In asynchronous communication, there is no separate clock line. Instead, both the sender and receiver operate at an agreed-upon baud rate, such as 9600 bits per second. Each side uses its own internal clock, which must be accurate enough to maintain synchronization over time. Although this approach simplifies wiring, since no clock line is needed, it typically supports lower data speeds compared to the synchronous method. Topology refers to how devices are physically or logically arranged in a communication network and how data flows between them. It defines the structure of connections, such as whether communication is direct, shared, or distributed across multiple nodes. The simplest form is a one-to-one connection, where two devices communicate directly. For example, a microcontroller connected to a single sensor through UART. This setup is straightforward, reliable, and ideal for dedicated communication between two endpoints. A one-to-many or multi-drop topology allows one master device to communicate with several slave devices on the same communication line. Examples include I2C and RS-485. In I2C, multiple sensors can share the same two wires, SDA and SCL, with unique addresses identifying each device. RS-485, on the other hand, supports longer distances and more robust differential signaling, often used in industrial systems. A many-to-many topology forms a full or partial network, such as Ethernet, where multiple devices can communicate with one another either directly or through intermediate devices like switches and routers. This structure supports routing, redundancy, and scalability, allowing the network to expand and reconfigure without major hardware changes. Each topology has its strengths and trade-offs. Simpler ones like one-to-one are easier to implement and debug, while complex topologies like Ethernet networks offer flexibility and high performance, but require more sophisticated management and infrastructure. This is one of the most important concepts in communication wiring: the difference between single-ended and differential signaling. In single-ended communication, data is transmitted through a single wire referenced to a common ground. It's simple and cost-effective, but more vulnerable to electrical noise and voltage drops, especially over long distances. Typical examples include UART and I2C, which operate at voltage levels such as 3.3 volts or 5 volts. In contrast, differential signaling uses a pair of wires, often labeled data plus and data minus, where the receiver compares the voltage difference between the two lines to determine the logic state. Because both wires experience similar noise interference, the differential comparison effectively cancels out common noise. This design makes differential systems highly tolerant to voltage imperfections, allowing them to maintain signal integrity over longer distances and in noisy industrial environments. Standards like RS-485 CAN and Ethernet use differential signaling to achieve reliable, high-speed communication. Converters such as SE to DE, single-ended to differential modules, are often used to interface single-ended microcontroller outputs with differential communication systems. This slide presents a timeline of key communication standards that have shaped the evolution of electronic and computer systems. Each standard was developed to solve specific challenges, such as data speed, transmission distance, reliability, or ease of connection. And together they form the foundation of modern mechatronic communication. ARS 232, introduced in the 1960s, was one of the earliest serial communication standards. It uses single-ended signaling and is designed for short-distance communication between a computer and a peripheral, such as a modem or microcontroller. Later, RS485 improved upon this by adopting differential signaling, allowing for longer distances and multiple devices on the same bus, making it suitable for industrial automation and distributed sensor networks. In the late 1970s and early 1980s, SPI, Serial Peripheral Interface, and I2C, Inter-Integrated Circuit, were developed for communication within a circuit board. SPI offers high-speed full-duplex communication between a master and multiple slaves, while I2C uses only two wires, SDA and SCL, for simple multi-device setups. Both remain essential for connecting sensors, displays, and memory chips to microcontrollers. CAN, Controller Area Network, introduced around 1983 by Bosch, revolutionized automotive and industrial systems by providing robust, differential, and message-based communication that tolerates electrical noise and supports multiple nodes without a central computer. At the same time, Ethernet emerged as the standard for local area networking, enabling reliable, high-speed data transfer between computers using packet-based communication. Over time, Ethernet evolved from 10 megabits per second to over 10 gigabits per second, supporting both data and power transmission through PoE, Power over Ethernet. In 1996, USB, Universal Serial Bus, simplified connectivity between computers and peripherals, replacing many legacy connectors. It supports both data and power transfer and is now the universal interface for consumer and embedded devices. More recently, wireless standards like Bluetooth, Wi-Fi, and Li-Fi have enabled cable-free communication. Bluetooth is ideal for short-range, low-power applications like wearable devices and sensors. Wi-Fi provides high-speed networking over longer ranges, and Li-Fi uses visible light for ultra-fast wireless data transmission in specific environments. By understanding when and why each of these standards was developed, and their advantages and limitations, you can make informed decisions when selecting the most appropriate communication protocol for your application, whether it's a small embedded system or a large industrial network. Serial communication is one of the most fundamental and widely used methods for data exchange between electronic devices. It operates using a minimal set of signals and parameters, making it simple yet highly effective for microcontroller-based systems. At its core, serial communication typically involves two main signal lines, TX, transmit, and RX, receive, which handle the sending and receiving of data along with a common ground connection. Data is sent one bit at a time in sequence, synchronized by timing parameters agreed upon by both devices. Several key parameters define how data is transmitted. Baud rate specifies the number of bits sent per second. Common rates include 9,600, 115,200, and higher depending on the device. Data bits indicate how many bits make up each data packet, usually 7 or 8 bits. Parity provides a simple error-checking mechanism to detect transmission errors. Options include even, odd, or none. Stop bits mark the end of a data frame, allowing the receiver time to prepare for the next byte. For example, a configuration labeled 9600-8-N-1 means 9600 baud rate, 8 data bits, no parity, and 1 stop bit, a very common standard in embedded systems. Because of its low wiring requirement, ease of setup, and reliable performance, serial communication forms the foundation of most communication interfaces used in the lab, such as UART, USB to serial, and even Bluetooth serial modules. It's the simplest way to send sensor readings to a computer, transmit control commands to a robot, or monitor data from microcontrollers in real time. The Arduino serial monitor is one of the most useful tools in microcontroller programming. It acts as a simple text-based terminal that allows you to send and receive data between your computer and the Arduino board through a serial connection. The monitor communicates via the UART interface, which uses the USB cable as a serial bridge. When you open the serial monitor from the Arduino IDE, it establishes a link that lets you exchange ASCII text data. This means the data is represented as readable characters rather than raw binary values. One of the main purposes of the serial monitor is debugging. By using commands like serial.print or serial.println, you can display variables, sensor readings, or status messages directly on your computer screen. This helps you understand how your program behaves in real time, detect errors, and verify that data is being processed correctly. The serial monitor also allows two-way communication. You can type commands or numbers in the input bar and send them back to the Arduino using the send button. The Arduino can then read the incoming data with serial.read open parenthesis or serial.parseInt close parenthesis, enabling simple interactive control. For example, turning on LEDs, changing motor speed, or adjusting parameters during testing. Because of its simplicity, the serial monitor is an excellent starting point for learning about serial communication. It helps bridge your code logic and the physical world, giving immediate feedback during experimentation and development. Serial communication can be broadly classified into two main types: asynchronous and synchronous. The difference lies in how the sender and receiver coordinate timing during data transmission. In asynchronous communication, there is no separate clock line. The devices rely on a common understanding of timing set by the baud rate, for example, 9,600 bits per second. Each data frame includes start and stop bits to mark where the transmission begins and ends. Only 3 wires are typically used: TX, transmit; RX, receive; and GND, ground. This simplicity makes asynchronous communication easy to implement and ideal for short, low-speed connections, such as UART, RS-232, and USB to serial adapters. However, because each byte requires start and stop bits and relies on local clocks that may drift slightly, the overall data rate is lower compared to synchronous methods. In synchronous communication, an additional clock line, SCLK, is introduced, and sometimes a slave select, SS line, when multiple devices are connected. The master device generates the clock signal, which ensures that both sender and receiver stay perfectly synchronized at each clock pulse. Data bits are transferred in rhythm with this clock, allowing continuous and faster transmission without the overhead of start and stop bits. This approach is used in protocols like SPI and I2C, which are ideal for connecting multiple sensors or peripherals to a microcontroller with high reliability and speed. In summary, asynchronous systems are simpler and easier but slower, while synchronous systems are more complex but faster and more precise, especially when multiple devices share the same communication bus. This slide shows 2 simple examples demonstrating the difference between asynchronous serial communication, UART, and synchronous serial communication, SPI, in Arduino. Even though both are forms of serial communication, they work quite differently at both the hardware and software levels. Let's start with the asynchronous serial example on the left. In this code, the serial dot begin open parenthesis 9600, close parenthesis command initializes the UART communication at a baud rate of 9,600 bits per second. Inside the loop, the program checks whether any data is available using serial.available. If data has been received, it reads the incoming byte with serial.read and then prints it back to the serial monitor using serial.print and serial.println. This is known as echoing, a simple way to verify that serial communication is working. Since UART is asynchronous, no clock line is needed. Both devices just need to agree on the baud rate, here 9,600. Now on the right, the SPI example demonstrates a synchronous method. The line include imports the SPI library and SPI.begin opens the bus. The chip select SS pin is configured as an output to choose which slave device is currently active. During data transfer, the master pulls the SS line low, sends data using SPI.transfer, and then sets SS high again when the transaction ends. SPI uses multiple lines: MOSI, MISO, SCK, and SS, and the clock signal, SCK, ensures that the sender and receiver stay perfectly synchronized. In short, the UART example shows simple, direct communication ideal for text and debugging, while the SPI example shows faster, synchronized data exchange suitable for sensors, memory chips, and displays. Together, they illustrate how the hardware configuration and timing mechanisms differ between asynchronous and synchronous serial systems. This slide builds on the previous examples and shows how serial communication can be implemented using Python on a PC and MicroPython on a microcontroller. Both follow the same communication principles, but differ slightly in how they interact with the hardware. Let's start with standard Python on a computer. The serial module, often provided by the PySerial library, allows your computer to communicate through serial ports such as COM1, COM3, or /dev/t/tyusb0 on Linux. By creating a serial object, for example, ser equals serial, .serial open parenthesis, COM1, 9600 close parenthesis, you establish a connection at a specified baud rate. The ser.read and ser.write commands allow your PC to send and receive bytes of data. This is especially useful when you want to send commands to a microcontroller, log sensor data, or build a GUI that interacts with embedded systems in real time. In the example shown, the program continuously checks for incoming data and prints it to the terminal, making it a simple UART monitor. On the other hand, MicroPython runs directly on embedded devices like the Raspberry Pi Pico, RP2040, ESP32, or similar boards. It provides hardware-level access to communication interfaces through the machine module. Here, the example shows how to initialize an SPI, serial peripheral interface bus using SPI equals SPI, open parenthesis, 0, baud rate equals 1 million, polarity equals 0, phase equals 0, bits equals 8, first bit equals SPI.MSB, SCK equals pin X, MOSI equals pin X, MISO equals pin X, and a chip select pin CS equals pin X, pin.out. The function read SPI data toggles the CS line, performs a synchronous data transfer using SPI.read open parenthesis 1 close parenthesis, and then releases the line. This MicroPython code demonstrates a device-to-device connection, for instance, reading data from a temperature sensor or display module, where the microcontroller acts as an SPI master. In contrast, the PC-based Python script shows PC-to-device communication, a higher-level connection where your computer acts as the master controller and interacts with an embedded device via USB or serial adapter. Together, these two examples highlight how Python can be used effectively across both levels. On a PC, to communicate and visualize data from embedded systems. On a microcontroller, to directly handle hardware-level protocols like SPI, I2C, or UART. This flexibility makes Python and MicroPython powerful tools for rapid prototyping, testing, and integrating mechatronic systems. In this session, we'll look at two fundamental hardware communication interfaces that allow microcontrollers and computers to exchange data efficiently: serial, UART, and SPI, serial peripheral interface. 1. Raspberry Pi and Arduino, serial communication. Let's begin with the Raspberry Pi Arduino connection. Both devices can communicate using UART, which transfers data one bit at a time over two lines: TX, transmit, and RX, receive. The Arduino Uno provides these on pins D1, TX, and D0, RX, while the Raspberry Pi uses GPIO 14, TX, and GPIO 15, RX. Because the Pi operates at 3.3 volts logic and the Arduino at 5 volts, a logic-level converter is essential to prevent damage and ensure reliable communication. The connection is straightforward. Arduino TX arrow, right arrow, H, V, TX on converter. Arduino RX arrow, left arrow, H, V, RX. Raspberry Pi RX arrow, left arrow, LV, TX. Raspberry Pi TX arrow, right arrow, LV, RX 5 volts from Arduino. HV, 3.3 volts from Pi, LV, and all grounds must be connected. Once wired, the Pi's serial port can be enabled via Raspi config. Interface options, serial port. The Arduino can then be programmed with a simple sketch that listens for incoming messages and echoes responses, while the Pi uses a Python script with the PySerial library to send and receive data through /dev/serial0. This setup creates a point-to-point link between the two boards, the Raspberry Pi as a master processor and the Arduino as a real-time controller handling sensors or actuators. Such hybrid systems are common in robotics and IoT, combining the Pi's computational power with the Arduino's precise timing control. 2. Arduino and sensor module via SPI communication. Next, we move to communication between an Arduino and a sensor or peripheral module using the SPI protocol. In this example, the Arduino Leonardo connects to an ENC28J60 Ethernet module, but the same wiring applies to other SPI devices, such as temperature sensors, flash memory, or displays. SPI is a synchronous full-duplex protocol that uses a shared clock signal for timing and consists of 4 key lines: MOSI, master out, slave in, data from Arduino to module MISO, master in, slave out, data from module to Arduino SCK, clock, synchronizes data transfer, CS or SS, chip select, enables one device at a time. In this setup, the Arduino acts as the master and the sensor as the slave. The wiring connections are VCC, 5 volts, GND, ground SCK, pin 13, MISO, pin 12, MOSI, pin 11, and CS, pin 10. During operation, when the Arduino sets CS low, communication begins. Each clock pulse shifts data out on MOSI while receiving data simultaneously on MISO. When the message is complete, CS is set high, ending communication. A simple SPI example code initializes the SPI bus, sets the CS pin, and transmits test data using SPI.transfer. This demonstrates synchronized high-speed data exchange, far faster than asynchronous serial communication. SPI is widely used for high-performance peripherals like displays, ADCS, DACS, or Ethernet controllers. It offers high-speed and full duplex operation, though it requires more pins than I²C. 3. Summary. To summarize, UART, serial, enables simple, two-wire, long-distance, point-to-point communication, ideal for connecting systems like Raspberry Pi and Arduino. SPI enables fast, synchronous communication between a master and multiple slave devices, perfect for sensors and modules requiring quick data exchange. Both methods are essential tools in mechatronics and IoT design. By mastering them, we can integrate multiple processors and peripherals into a cohesive, intelligent system, where data flows seamlessly from sensors through controllers to decision-making nodes like the Raspberry Pi. And that's how we combine serial and SPI communication to create robust, multi-layered embedded systems for modern applications. SPI, or Serial Peripheral Interface, is a high-speed serial communication protocol originally developed by Motorola in the 1980s. It is a synchronous full-duplex interface, meaning that data can be transmitted and received simultaneously, and all communication is synchronized using a clock signal generated by the master device. In a typical SPI setup, there is one master and one or more slave devices. The master controls the clock, SCK, and selects which slave to communicate with using a chip select CS or slave select SS line. The main connections are MOSI, master out, slave in, carries data from master to slave. MISO, master in, slave out, carries data from slave back to master. SCK, serial clock, synchronizes data transmission. SS or CS, slave select, used by the master to activate a specific slave device. SPI is extremely popular because it offers high data transfer speeds and a simple hardware design. It doesn't require complex addressing or arbitration logic like I²C. It's commonly used to connect sensors, displays like OLED or TFT panels, memory cards, SD cards, flash chips, and other peripherals that require rapid data exchange. One major advantage of SPI is its full duplex nature. Both the master and slave can send and receive data simultaneously. This makes it much faster than asynchronous protocols such as UART. However, the downside is that SPI uses more wires, especially when multiple slaves are involved, since each one needs its own chip select line. This limits scalability compared to multi-drop buses like I²C. Another key benefit is flexibility. SPI allows custom clock speeds, polarity, and phase settings, commonly referred to as CPOL and CPHA, to match the timing requirements of different devices. For example, you can configure SPI modes 0 to 3, depending on when data is sampled and shifted relative to the clock signal. In practical mechatronic systems, SPI is ideal for short-distance, high-speed communication inside a PCB or between modules. When we use an SD card module or an OLED display in Arduino or Raspberry Pi Pico projects, we're most likely communicating through SPI. Overall, SPI combines speed, precision, and simplicity, making it one of the most essential protocols in embedded system design. When configuring a serial communication interface, several parameters and physical concerns must be carefully checked to ensure that data transfer is reliable and error-free. Let's go through each of them, one by one. First, the COM port ID. This identifies which physical or virtual serial port your device is using. For example, on Windows, it might appear as COM1 or COM3, while on Linux or Mac OS, it may show as /dev/TTYU-SB0 or /dev/TTYS1. Choosing the correct port ensures your software is communicating with the right hardware. Next is the baud rate, data bits, and parity, which together define the data frame format, commonly written as 9600-8-N-1. That means 9,600 bits per second, 8 data bits, no parity bit, and 1 stop bit. Both devices must have identical settings, otherwise, bits will be misinterpreted, leading to corrupted data. The terminator, such as CR-LF or CR/LF combination, indicates the end of a message or line of text. This is particularly important when sending or receiving strings. For example, when reading sensor data or sending commands from a computer terminal. Next, we have byte order, also called endianness. This determines how multi-byte data, like integers or floats, is arranged in memory. Little endian means the least significant byte comes first, used by most microcontrollers. Big endian means the most significant byte comes first, common in some network and industrial systems. If both devices use different byte orders, you'll receive scrambled data unless you perform proper conversion. Another aspect is whether your system transmits binary or ASCII data. ASCII communication sends human-readable characters, for example 1, 2, 3, while binary communication sends raw byte values. When working with binary data, you might need data casting, converting between data types, like int, float, or byte, to ensure correct interpretation of values. Then comes hardware versus software serial. Some microcontrollers have built-in hardware UARTs, which are faster and more stable. If hardware ports are limited, a software serial library can simulate UART on regular digital pins, though it's slower and less accurate, especially at high baud rates. You must also verify logic-level compatibility. Microcontrollers and communication devices operate at different voltage levels. 3.3 volts, LVTTL, used by ESP32, Raspberry Pi Pico, etc. 5 volts, TTL, used by Arduino Uno and many older boards. 12 volts, RS232, used in PC serial ports and industrial interfaces. Directly connecting mismatched voltage levels can permanently damage low-voltage devices, so logic-level shifters are often used. Another practical wiring issue is TX-RX orientation. Remember, the TX transmit pin of one device must connect to the RX receive pin of the other. Connecting TX to TX or RX to RX will result in no communication, a very common beginner mistake. Finally, many UART systems include a FIFO, first in, first out, buffer to temporarily store incoming or outgoing bytes. This buffer helps prevent data loss when the processor is busy with other tasks, improving communication stability in high-speed or multitasking systems. In summary, serial communication might look simple, just a few wires, but behind it are many small details that must be set correctly. Baud rate, format, voltage, and wiring all need to match precisely for your data to be transmitted cleanly and consistently. When working with microcontrollers and sensors, one of the most critical hardware considerations is voltage compatibility between devices. Different systems operate at different logic levels. For example, An Arduino Uno uses 5-volt TTL logic, while many modern sensors, modules, and microcontrollers like the ESP32 or Raspberry Pi Pico RP2040 use 3.3 volts logic. If a 5-volt device sends a logic high signal directly into a 3.3-volt input, it can exceed the voltage tolerance of that circuit and damage the lower voltage device. To prevent this, we use a logic level converter, sometimes called a level shifter. A logic level converter acts as a translator between two voltage domains, ensuring that both devices can communicate safely and correctly. For example, when connecting an Arduino 5-volt logic to a 3.3-volt sensor or display, the converter steps down the voltage on the TX or SCL/SDA lines from 5 volts to 3.3 volts. Similarly, it can step up the return signal from 3.3 volts to 5V so the Arduino can recognize it as a high. There are two main types of level converters: unidirectional converters, which allow signal flow in only one direction. These are suitable for one-way communication lines like TX, transmit, or SPI MOSI. Bidirectional converters, which allow signal flow in both directions automatically. These are ideal for two-way buses, such as I2C, where the same line is used for both sending and receiving data. In some cases, resistor-based voltage dividers can be used as a simple, low-cost alternative for slow-speed unidirectional signals. However, for high-speed or bidirectional protocols like I2C or SPI, dedicated MOSFET-based level shifters are preferred because they maintain proper signal integrity and timing. It's also important to note that logic level conversion is different from power regulation. The converter only adjusts digital signal voltages. It does not provide power to the device. You must still supply the correct power voltage, for example, 3.3 volts to the sensor's VCC pin. In summary, level converters play a vital role in protecting circuits and enabling communication between mixed voltage devices. They are a small but essential component in mechatronics and embedded system design, ensuring that 5-volt and 3.3-volt systems can safely and efficiently exchange data without the risk of electrical damage. In digital communication and programming, it's crucial to understand how data is represented, interpreted, and exchanged between systems. Two key concepts that often come into play are data casting and data conversion. Although they sound similar, they serve different purposes and occur at different levels of data processing. Let's begin with data casting. Data casting is the process of temporarily reinterpreting one data type as another within the same program or system. It doesn't actually change the underlying bits stored in memory. It only changes how those bits are read or interpreted by the program. For example, in C or Python, you might have a variable that stores a byte of data from a sensor. Unsigned char value equals 0x41. If you cast this byte to a character, the same data, 0x41, would be displayed as the ASCII character A. Or if you cast it to an integer, it would be interpreted as the number 65. In other words, casting changes perspective, not the actual content. This is useful when reading mixed-type data from memory or buffers, such as when bytes received through UART need to be interpreted as floats, integers, or strings. Now, data conversion goes a step further. Conversion involves transforming data from one structure, type, or format into another, sometimes even across different systems. For example, you might convert a numerical sensor reading into a human-readable text format before sending it over a serial connection. Or you might transform data between file formats, say converting from CSV to JSON, or from binary to ASCII, to match the communication protocol or data storage requirements. In embedded systems, conversion often happens when interfacing between devices with different data representations. For instance, a microcontroller may send integer temperature values over I2C, while the receiving software on a PC converts those integers into floating point Celsius readings or formatted display text. Both casting and conversion are vital for reliable communication. Casting ensures data is interpreted correctly within a system. Conversion ensures data is formatted correctly between systems. Understanding the difference prevents miscommunication between devices and avoids typical errors like garbled text, incorrect numerical values, or mismatched byte ordering. I2C, which stands for Inter-Integrated Circuit, is one of the most common communication protocols used for connecting multiple devices on the same circuit board. It was originally developed by Philips, now NXP Semiconductors, in 1982 and is still widely used today because of its simplicity, flexibility, and low pin count. The I2C bus uses only two wires for communication. SDA, serial data, carries the actual data being transferred. SCL, serial clock, provides timing signals that synchronize the communication. Despite using just two lines, IC supports communication between multiple devices, including multiple masters and multiple slaves, all connected to the same bus. Each device has a unique 7-bit or 10-bit address, allowing the master to identify which slave it wants to communicate with. When communication starts, the master generates a start condition and sends the address of the target slave. If a device recognizes its address, it responds with an acknowledge ACK signal, confirming that it's ready to communicate. Data is then sent in 8-bit frames, followed by an acknowledgement bit after each byte. Finally, the master sends a stop condition to end the communication session. One key advantage of I2C is that it allows many devices to share the same two wires, reducing wiring complexity significantly. For example, you can connect an OLED display, a temperature sensor, and an accelerometer to the same SDA and SCL lines of a microcontroller. This makes I2C particularly well-suited for compact embedded systems, sensor arrays, and mechatronic projects where PCB space is limited. However, because all devices share the same bus, I2C is best for short-distance and moderate-speed communication, typically up to 400 kHz standard mode or 1 MHz fast mode. Over longer distances, the capacitance of the bus wires causes signal distortion and limits performance. I2C also uses pull-up resistors on both SDA and SCL lines to maintain stable voltage levels. These resistors ensure that the bus remains high when idle and allow devices to pull the line low when sending bits. Without proper pull-up resistors, the communication may fail or become unreliable. In summary, I2C is an elegant and efficient solution for linking multiple components such as sensors, displays, and EEPROMS, using only two signal lines. It's slower than SPI but requires far fewer wires, making it a perfect choice for low-speed, short-range communication within a circuit board. USB, or Universal Serial Bus, is one of the most successful and widely adopted communication standards in the world. It was designed to replace a variety of legacy ports, such as serial, RS-232, parallel, and PS2 connectors, and to simplify how computers connect to peripherals like keyboards, mice, storage drives, printers, and microcontrollers. The key idea behind USB is universality. It provides a standardized interface that supports both data transfer and power delivery using the same cable. For example, when you plug in an Arduino, a USB camera, or a phone, a single USB cable not only exchanges data but also powers the device. USB communication is host-controlled, meaning one device acts as the host, typically a PC or hub, and all others are peripherals or devices. This host manages data transfer timing, device addressing, and power distribution. Modern systems can include USB hubs that expand the number of ports, allowing multiple devices to operate simultaneously under one host. One of USB's most convenient features is plug-and-play operation. When a new USB device is connected, the host automatically detects it, reads its identification through a process called enumeration, and loads the appropriate driver. No manual configuration required. This self-configuring ability made USB incredibly popular for consumer and industrial electronics. Over the years, USB has evolved through multiple generations, each offering faster speeds and improved functionality. USB 1.0, 1996. Up to 12 megabits per second. USB 2.0, 2000. Up to 480 megabits per second. Still common today for many microcontrollers. USB 3.0/3.1/3.2. Introducing the blue connectors and super speed transfer up to 20 gigabits per second USB 4, 2019. Leveraging Thunderbolt 3 technology, reaching over 40 gigabits per second with reversible Type-C connectors. USB also supports multiple modes of power delivery. The traditional USB 2.0 port can supply up to 500 milliamps at 5 volts, while newer USB-C ports can deliver up to 100 watts, 20 volts times 5A, through USB power delivery PD negotiation. This makes USB not just a data interface, but also a major power interface for laptops, displays, and embedded devices. In embedded systems and mechatronics, USB is often used in three key roles: programming and debugging interface, such as connecting an Arduino or RP2040 board to upload firmware; communication link, for serial data exchange between a PC and microcontroller, using USB to UART bridges like CH340 or CP2102; peripheral connection, where the microcontroller acts as a USB device, e.g., appearing as a keyboard, mouse, or virtual COM port. In summary, USB has become the global communication backbone for modern electronics. It combines high-speed data, flexible power delivery, automatic configuration, and wide compatibility, all through a single, easy-to-use connection standard. Ethernet is one of the most important and long-standing communication standards in the world, and it forms the backbone of most local area networks, LANs. It was first developed in the 1970s by Xerox, Intel, and DEC, and has evolved into a robust, high-speed, and highly reliable communication system used everywhere from offices to factories and embedded systems. Ethernet is based on packet-switched communication, meaning that data is broken into small packets and transmitted over the network cable. Each packet includes source and destination addresses, MAC addresses, allowing many devices to share the same network medium efficiently. This enables many-to-many communication. Multiple computers, controllers, and sensors can exchange information simultaneously through routers or switches. One of Ethernet's key strengths is speed. Early Ethernet operated at 10 megabits per second, but over the decades, it has advanced through 100 megabits per second, fast Ethernet, 1 gigabit per second, gigabit Ethernet, 10 gigabits per second, and now up to 400 gigabits per second and beyond in data centers. For industrial and IoT applications, 100 megabits per second and 1 gigabit per second Ethernet remain the most common, providing a reliable and fast connection for real-time control, data logging, and monitoring. Ethernet also offers long-distance capability. Unlike short-range protocols like I2C or SPI, Ethernet can span up to 100 meters using twisted pair cables, Cat5e, Cat6, or much farther with fiber optics. This makes it ideal for large-scale mechatronic systems, smart factories, and remote sensing networks. Another major advantage is reliability. Ethernet uses error detection via CRC checks and automatic retransmission to ensure that data arrives correctly. Modern network switches further isolate communication paths, preventing collisions and ensuring stable, full-duplex data transfer. A powerful extension of Ethernet is Power over Ethernet, PoE. PoE allows both data and electrical power to be delivered through the same cable, typically up to 90 watts in the latest standards, IEEE 802.3BT. This simplifies installation and reduces wiring, especially for devices like IP cameras, industrial controllers, Wi-Fi access points, and IoT sensors. With PoE, there's no need for a separate power adapter. One Ethernet cable handles everything. In mechatronics and automation, Ethernet plays a key role in industrial networking protocols such as EtherCAT, Modbus TCP, and Profinet, which provide deterministic, real-time communication between controllers and actuators. These systems extend Ethernet's capabilities to meet the stringent timing and safety requirements of industrial environments. In summary, Ethernet combines high speed, long distance, scalability, and robustness in one universal communication standard. It's not just for office computers, it's the foundation of modern connected systems, from industrial robots to smart agriculture and IoT networks. To conclude today's session, we have explored the full landscape of communication methods that enable seamless interaction between microcontrollers, sensors, computers, and actuators, forming the essential backbone of every mechatronic and embedded system. We began by revisiting the fundamentals of data transfer, distinguishing between serial and parallel communication, and understanding how information travels either one bit at a time or through multiple lines simultaneously. Serial communication, with its simplicity, robustness, and noise resistance, has become the dominant approach in modern embedded design. From there, we examined the major wired communication standards that connect hardware components, UART, Universal Asynchronous Receiver Transmitter, a simple point-to-point protocol widely used for debugging and serial interfacing. SPI, Serial Peripheral Interface, a high-speed, full-duplex protocol suited for sensors, SD cards, and displays. I2C, Inter-Integrated Circuit, a two-wire protocol that allows multiple chips to communicate efficiently on a single bus. USB, Universal Serial Bus, a versatile interface that carries both power and data central to peripheral and microcontroller connections. Ethernet, the foundation of high-speed networking, supporting long-distance data transfer and power delivery via PoE. Along the way, we emphasized key design considerations: logic-level compatibility, voltage matching, data casting, and proper pin configuration, since even the most sophisticated protocol depends on accurate electrical interfacing to function correctly. We also connected these wired approaches to the world of wireless communication, including Wi-Fi, Bluetooth, Zigbee, and Li-Fi, which extend connectivity beyond cables and form the basis of distributed and IoT-based systems. Each communication method carries its own balance of speed, distance, complexity, and reliability, allowing engineers to select the most suitable protocol for their specific application. In the bigger picture, communication is the bridge between sensing, computation, and actuation. It closes the cyber-physical loop, transmitting data from sensors that perceive the environment to processors that analyze information and to actuators that execute physical responses. A practical example of this can be seen in a robot powered by 5 Dynamixel motors, which all communicate through a half-duplex serial bus. Using a single communication line, the controller can send commands and simultaneously receive feedback on motor positions and states. This bus architecture not only simplifies wiring, but also enables precise and coordinated motion control through a robust, efficient protocol. Ultimately, understanding these communication principles allows us to design systems that are modular, scalable, and intelligent, where multiple components operate together as one coherent unit. In short, communication is what brings mechatronic systems to life, transforming isolated elements into an integrated, responsive, and autonomous whole. This slide shows a practical MicroPython example of I2C communication between a Raspberry Pi Pico and an OLED display. It's a great illustration of how high-level code can make device-to-device communication both simple and reliable. Let's walk through what this program does. First, the script imports the necessary MicroPython modules: machine for hardware control, SSD 1306 for the OLED driver library, and UTIME for timing functions. These libraries give the Pico direct access to its I2C bus pins and to standard display commands. Next, the code initializes the I2C interface. The line I2C equals machine.I2C open parenthesis 0, SCL equals machine.pin open, parenthesis 1 close parenthesis comma SDA equals machine.pin, open parenthesis 0 close parenthesis comma, FREC equals 400,000. Close parenthesis configures the Pico's I2C bus 0 to use GPIO0 SDA and GPIO1 SCL at 400 kHz. This frequency, known as fast mode, is typical for small displays and sensors. After initialization, the command devices equals I2C.scan scans the bus for all connected I2C devices. Each device responds with its unique 7-bit address, allowing the Pico to identify what's connected. For example, an OLED module based on the SSD 1306 controller often appears at address 0x3C. This scanning step is useful in troubleshooting, as it confirms that the wiring and pull-up resistors are correct. Once the OLED address is detected, the code creates a display object using old equals ssd1306.ssd1306 C open parenthesis 128, 64, I2C close parenthesis. This tells MicroPython the display size, 128 by 64 pixels, and links it to the active I2C bus. From this point, you can use simple commands such as OLED.text open parenthesis to draw characters and OLED.show open parenthesis to update the screen. In this example, the Pico writes a short text string to the display. For instance, "Hello Pico," and then refreshes it with OLED.show. That single operation demonstrates an entire I2C transaction. The master, Pico, sends data packets over SDA and SCL to the slave, OLED, which decodes the bytes into visible pixels. This exercise illustrates several important engineering principles. Address-based communication. Multiple devices can share the same two wires as long as each has a unique address. Master-slave protocol. The Pico controls the clock and decides when data moves. Practical debugging. Scanning and verifying device addresses helps diagnose wiring or power issues. In real applications, this same technique extends far beyond displays. You can use I2C to read temperature sensors, accelerometers, real-time clocks, or even connect DACS and ADCS. So this short script encapsulates the entire workflow of I2C communication in MicroPython: detect, initialize, write, and display, bridging theory with real-world implementation. In communication systems, it's essential to understand that there are two layers of protocols working together: the hardware protocol and the software protocol. Each plays a distinct but complementary role in ensuring that data moves accurately and meaningfully between devices. Let's start with the hardware protocol. This layer defines the physical and electrical behavior of the communication interface. In other words, how signals actually travel through wires or connectors. It deals with details like voltage levels, for example, 0 to 5 volts in TTL logic, plus or minus 12 volts in RS-232, or differential signaling in CAN and Ethernet. Timing and synchronization, how fast data bits are transmitted, baud rate, clock cycles. Pin assignments, which pin is used for transmitting, receiving, or clock signals. Signal shape and polarity, whether data changes on a rising or falling clock edge. In short, the hardware protocol ensures that two devices can physically understand each other's signals. It is the foundation. Without the right wiring, voltage, and timing, no meaningful data can be exchanged, no matter how perfect the software is. On top of this lies the software protocol, which defines how information is structured, addressed, and verified once it is transmitted over the hardware link. The software protocol specifies data framing, where a message starts and ends; addressing schemes, identifying which device the message is for, like I2C addresses or Ethernet MAC addresses; command and response format, defining what the data actually means; error detection and correction, using checksums, CRC, or parity bits to ensure data integrity; flow control and acknowledgement, making sure messages aren't lost or duplicated. For example, in UART, the hardware protocol defines TX/RX pins, voltage levels, and timing, while the software protocol defines data frames like start bit, 8 data bits, parity, stop bit. In Ethernet, the hardware defines the physical layer, cabling, voltage, timing, while the software protocol defines higher-level operations like IP addressing, TCP/UDP packets, and data validation. Together, these two layers form what we call a communication stack, the complete system that moves raw electrical signals all the way up to meaningful information. You can think of it like human communication. The hardware protocol is the sound of the voice or vibration of air that carries the message. The software protocol is the language or grammar that gives those sounds meaning. If the hardware layer fails, the signal doesn't reach the destination. If the software layer fails, the signal arrives but is meaningless. Only when both work in harmony can reliable, structured communication occur, whether it's between two chips, two computers, or two industrial robots. When designing or selecting a communication system, one of the key considerations is whether the communication medium, the physical connection or transmission path, is shared or dedicated. This determines how multiple devices access the channel, how data collisions are handled, and how predictable the communication timing will be. Let's start with shared systems. In a shared system, multiple devices use the same bus or communication channel, taking turns to transmit data. Only one device can send information at a time, while others must wait for their turn. This arrangement significantly reduces wiring complexity and cost since all devices share the same lines. A great example is the I2C bus. Here, many sensors and peripherals share just two wires, SDA for data and SCL for the clock. But each device has a unique address. The master device controls the timing and decides which slave can talk, preventing two devices from transmitting simultaneously. Similarly, in Wi-Fi networks, multiple devices share the same wireless medium. Access is managed by a protocol, like CSMA/CA, Carrier Sense Multiple Access with Collision Avoidance, that ensures devices transmit data only when the channel is clear. The main advantage of shared systems is scalability and efficiency. Adding more devices doesn't require more wiring. However, they can face bandwidth limitations and latency since communication time must be divided among participants. If many devices attempt to transmit simultaneously, data collisions or delays can occur, requiring retry mechanisms and timing control. On the other hand, dedicated systems use a one-to-one communication link. This means the channel is reserved exclusively for communication between two devices. Because the connection is not shared, there's no need for addressing, bus arbitration, or collision handling. Examples include UART serial communication, where a microcontroller's TX pin connects directly to another device's RX pin, forming a simple point-to-point link. Similarly, USB connections are effectively dedicated channels. Each USB device communicates directly with the host via its assigned data lines. This ensures consistent, uninterrupted, and high-speed communication. Dedicated systems offer high reliability, predictable timing, and low latency, making them ideal for real-time control or applications that demand continuous data flow, such as motor control, streaming sensors, or robotic actuators. The trade-off, however, is reduced scalability. Each new device typically requires its own physical connection, increasing wiring and hardware requirements. In short, shared systems are excellent for connecting many low-speed or occasional devices efficiently, while dedicated systems are best for high-performance, time-critical communication between fixed pairs of devices. In mechatronic and IoT system design, engineers often combine both types, using shared buses like I2C for sensors and dedicated channels like UART or SPI for high-speed or high-priority modules. Balancing these trade-offs is key to building a communication architecture that is both efficient and reliable.